What's going on, everybody? Mr. Diamond, still with bad audio quality. And today we're going to be going over the notes for predicting ions. Now, you are going to need your periodic table close by. If you didn't figure out from the last videos, we're going to be talking about the periodic table this whole chapter. And in this case, this is one of, if not the most important thing from this chapter. Valence electrons are important. Being able to predict the trends are going to be important. But this is the piece. You have to know this. You need to be able to do this to succeed in the future of this class. Please make sure you pay attention to this. Okay, that warning out of the way. Our next set of trends are focusing on ions. We've already discussed that in some detail. Just a reminder, they're any charged atoms. There are actually two types of ions, though. There are cations, which are positive. That's how I remember it, because cats have paws. Any atom that loses electrons is called a cation. These tend to be metals. Now remember, metals are the things that are found on the table this side of the staircase. The metalloids are all right here, metals are all over here, nonmetals are all over here. Anions are negative. Sorry, nothing clever, as cations are positive. Any atom that wants to gain electrons is called an anion. These are going to tend to be nonmetals. So again, nonmetals are the things over here. You've got like carbon, nitrogen, oxygen, chlorine, krypton, all of these things. Those are going to tend to be anions, although not krypton, as we'll discuss in a second. Before we discuss numbers and charges, we have a question to answer. Why? Why do atoms lose or gain electrons? And understanding why is going to tell us how these things are going to occur, or what's going to happen whenever they do gain or lose electrons. Most ions form because atoms at the core of it are lazy, needy little balls of stuff. They want to be stable, and they want to have low energy, and they want to do as little work as possible to get that accomplished. So to achieve this, they're going to try to have their electrons become stable, less reactive, in a stable and less reactive configuration. So who on the table would they want to be like? Who is the model citizen? Enter the noble gases. Now, I have UUO. I guess technically now we know it's OG oganescent or whatever it's called. But the noble gases are the cool kids of the table. They are stable. They have low energy. They are low reactive. If literally anything happens, the noble gases do not care. They're not here for that. So the goal of all the other elements is to be like that. They want to not have to do work. They want to not have to do anything. They want to be able to be lazy. So elements are usually going to try to look like a noble gas. Now the question is, how can they become like the noble gases? Well, can they change the protons? Yeah, but then the element changes. If sodium loses a proton, it just is neon. It's not like a noble gas. It literally is neon. Can neutrons change? Well, yeah, but then the properties don't change. It just becomes an isotope. You've got like carbon-12 becoming carbon-20. That's a big change, but that's just an isotope. It's still carbon. Can the electrons change? There we go. We've got our answer. Electrons have the most energy of the particles, and they're the most likely to interact, so they're the ones that can change. Instead of getting the element to change into the noble gas, it's going to try to make its electrons on the outside look like a noble gas's electrons. Since the electrons of all noble gases have something in common, a full octet, that's the goal. Ions are going to try to make it so that they have a full outer valence electron layer. So metals are going to try to lose electrons, because if they lose electrons over here, they're going to be moving backwards towards the noble gases. And then nonmetals are going to try to gain, because they're going to try to move this direction, because they're going to try to gain to get closer to the noble gases. So, for example, what would be the most likely charge for oxygen to have as an ion, and why? So things to consider is the metal or nonmetal, an electron configuration or its valence electron count, and what does it want to do? So oxygen is a nonmetal. It's right here up on the periodic table. It's right there. It's a nonmetal, so it's going to want to gain electrons. That means it's going to become an anion. The amount of electrons it's going to attempt to gain is going to be, well, oxygen's right here. Right now it has 1, 2, 3, 4, 5, 6 electrons. I really hope I'm centered, otherwise this is really awkward. 6 electrons. So it's going to want to gain 1, 2 more. and that means that it will have 8 electrons if it gains 2 more. And because electrons are negative, if it gains 2 electrons, it will then have a negative 2 charge. But we'll actually usually write that as a 2- charge because scientists like making things complicated. Okay, so what about for magnesium? So let's go up here. Magnesium is Mg. It's right there. Again, we're going to consider metal or non-metal, electron configuration. What does it want to do? Magnesium is a metal, so it's right here. So it's going to attempt to lose electrons. If it loses 1 electron, it'll have electrons like sodium. If it loses 1 more electron, it'll have electrons like neon. So it's going to actually try to drop to a lower energy level because at that lower energy level, it's got all 8 of its electrons. Since it currently has 2 out of 8, it's going to lose those 2 electrons. Since it lost something that is negative, it's going to have a positive charge. So it lost 2 negative things. That means it's going to have a +2 charge. So what are the predicted charges for each of the following elements? Go ahead and pause it if you're interested in seeing if you can figure them out by yourself. I'm going to take a drink of this Diet Mountain Dew here, and then I'll answer the question. Okay, so for aluminum, got all the answers up there. Aluminum is a +3 charge. It is a metal. Now it's really close to that staircase right there, but if you just remember, it's aluminum. Aluminum is a metal. So aluminum is right here. It is 1, 2, 3 steps away from being like neon. It needs to lose 3, so it's going to be a +3 charge. Carbon is on the other side of the staircase. It's a non-metal, so it needs to gain 1, 2, 3, 4 electrons, so that's a -4 charge. Potassium is a metal because it's on this side of the staircase, so potassium is going to want to lose 1 electron to be like argon up here. Helium is a noble gas, so it doesn't want to do anything. But notice that for iron, for Fe, this bad boy right here, I have a question mark. And you might go, wait a minute, iron is unknown? Well, the transition metals in the F block elements are a little bit weird. See, we know they have 2 valence electrons, but there's a lot of more complicated things at play in the F block or in the D block involving stability and like having electrons exchange energy levels. You've probably noticed this in the periodic table I pulled up with all of the orbital configurations and in the Z-space stuff. Both of those you've probably noticed, like some of them were a little bit weirder than what you expected. The exact reason is not important. Just know that you will need more information to determine them. Everything in the D block and the F block, you'll have to either be told or you'll have to be given enough information to solve for what its charge is. There are a few exceptions to this though. Zinc and cadmium, which are these 2 bad boys right here, they're right on the very end. Zinc and cadmium are always +2, and then silver down here, Ag, is always +1. Exact reason you don't need to know, but you just need to memorize that exception. I usually memorize that it's, so the staircase was right here for making something a metal or a non-metal. It's a little staircase off the staircase where aluminum is +3, these are +2, and then silver is +1. So here we go. We've got our trends. Now Ga is also +3, but that it just follows the silver, or I mean aluminum is the only one that's like tricky because it's really close to the staircase. So all of these would tend to be +1. These are +2. Silver is also +1. These guys are +2. These guys are +3. Technically, these guys down here would be +4, and sometimes they can be other things too. We'll talk about that a little bit later also. These guys are -3. These are -2. These are -1. But all of these blue space ones down here, all of these guys down here have multiple possible options. So when we get to our next chapter, we'll talk about how you can actually solve for those options. But things like thallium and lead and tin and bismuth, all of those, they get a little more complicated, so we have to do something else to actually identify those. In the meantime, though, that helps you identify ionic charges. Again, +1s, +2s, all of these guys down here are pretty much all something you'll have to either be told or you'll have to solve for. Silver is +1, cadmium and zinc is +2, aluminum and technically gallium, but we're not worried about that one. That doesn't show up as much, is +3. Then you get over here, fluorine, chlorine, bromine, iodine is -1. These guys are -2. These guys are -3. Carbon we'll consider -4, and boron we'll usually consider -5, just for simplicity's sake. So I hope that makes sense. If you have any questions, please let me know. Otherwise, this is Mr. Diamond signing off. I hope you have a great rest of your day, everybody.